Handsome young man tries to enter his house. Turns out he is locked out, just like he does for his studies.
This is an enzyme, and this should be the only video you're watching to learn about them. Why am I locked out of my own house? Because the locks don't fit my keys. Let me explain. An enzyme is a biological catalyst, meaning it speeds up reactions without participating in them. Each enzyme carries out a very specific reaction to break down what's known as a substrate into simpler products. For example, amylase in your saliva breaks down complex carbs into simple sugars. So, how does a reaction work then? To visualize this, there are two models we should know. Focus. The lock and key model states that the enzyme is perfectly shaped for the substrate. Just like... there we go. However, this isn't fully the case. You see, proteins aren't fully rigid, so when the substrate binds to the enzyme, it slightly alters its shape to fit. This is the induced fit model. The exact place the substrate binds is known as the active site. The substrate locks in and its activation energy is lowered so that it can begin to break down. Once these products are formed, they can detach from the active site and other substrate molecules can bind. The reactions can occur again and again if and only if the enzyme is fully intact. They are very sensitive to environmental changes. Let's, break this down. Temperature is the first factor which affects enzymatic activity. As the temperature increases, the kinetic energy or movement of molecules also increases. This makes them more likely to collide with each other in the correct orientation and thus induce the reaction. But wait, why does it decrease here? After reaching an optimum temperature, where it's just right for maximum collisions, it becomes too hot to handle for the enzyme itself, just like me. So it begins to denature and break down. The active site is disfigured and no longer can react with the substrate, and hence we get that decrease. So as the temperature increases, the enzyme activity also increases until reaching a saturation point, after which it decreases back to zero. The same trend can occur for pH. What's that? It's the concentration of hydrogen ions in the solution. Every enzyme resides in a different environment in the body. That's the pH at which the enzyme functions best. If the pH is too high or too low, basically deviating from the optimum, the enzyme activity decreases. Hydrogen ions alter the way the proteins fold to make the enzyme, disrupting its tertiary structure. Thus, the enzyme denatures. So, as the pH increases, the enzyme activity will also increase until it reaches an optimum, after which it decreases back again. Next, we got substrate concentration, which is the amount of substrate molecules. Each enzyme can only take one substrate at a time. So, if it reaches an excess, it's called a saturation point, after which no more substrate can bind. This can happen the other way around, where as the enzyme concentration increases, the activity increases until reaching a saturation point. Pretty straightforward. Okay, take a look at this outlet. If I want to plug my phone charger into it, but the fan's already plugged in, I can't charge my phone. That's a competitive inhibitor. They compete with the substrate molecule for the enzyme's active sites. Competitive inhibition slows down enzyme activity. Let's go back to the outlet. If I have this cable and try and plug it right next to here, this is preventing me from doing so. That's a non-competitive inhibitor. It attaches elsewhere on the enzyme, known as the allosteric site, and hence it alters the shape of the active site. The jigsaw doesn't work. Perfect. We also have activators, which do the opposite thing. They increase enzyme activity by changing the shape of unfit active sites. And there you go. Okay, if you enjoyed this teaching style, check out my video on DNA over here. Share this with a friend failing their bio exams. This is A.B.S.E signing out. Take care and... crap!